Hello, welcome to our next video. Okay, so by the way, don't forget, if you haven't subscribed to our channel yet, don't forget to click the subscribe button and ring the bell and select all so that you will be updated with our recent uploaded videos. So we will be uploading videos from time to time. Okay. Okay, so we will discuss vertical curve, symmetrical parabolic curve. So ano ba to? Saan ba to ginagamit, no? So this is used to connect two different grades, vertical, not horizontal. So we use parabolic curve, not circular curve. For the very simple reason that the parabolic curve is the only curve that changes in grade at uniform rate. Uniform rate yung pag-change ng grade niya, uniform with respect to the distance, horizontal distance. So this is the most ideal shape of curve to connect vertical curves. All right. So in this lecture, we will be discussing how to locate the summit of the curve, the elevation of the summit, the elevation and grade of any point on the curve. And then we will use the solution that we'll be using is using the grade diagram or using analytic geometry. Okay, so we have here our problem. A 3% grade at station 10 plus 100 meters is to be connected to a negative 2% grade at station 10 plus 420 using a symmetrical parabolic curve. If the tangent grades intersect at elevation 152 meters, evaluate the following. Okay, so first the location of the location and elevation of the summit of the curve, the elevation and grade of the curve at station 10 plus 200, and the elevation of the end of the vertical curve, EVC, or sometimes we call it PT. Okay, so let's draw the curve, schematic diagram. So we have here our initial grade, 3% grade at station 10 plus 100. So this the unit we are using is meter. So 10 kilometers, so 10 kilometers plus 100 meters. All right. And then we will, that's 3%. We will connect it to a negative 2% grade. Negative 2% grade at station 10 plus 420. And it was stated here, there is no elevation given here. And it was specified here that we will use a symmetrical curve. Symmetrical curve. So the elevation here will just adapt to the shape of the symmetrical parabola. All right. So this is the grade of the slope of the end of the curve. So G2 is G2. All right. So the stationing here is 110 plus 100, and this is 10 plus 420. So therefore, the distance between this curve, the length of the curve, is 320. That's the length of the curve. Now you might wonder, how come that is a horizontal length while this is a different elevation? Well, to answer that, actually, the length of the curve, the curvature, the length of the curve along the curve is very negligible. The sag for parabolic curves used in connecting grades is very small. So that the length of the curve, the length along the curve is approximately equal to the horizontal distance between the endpoints. So, all right, this is 320. This is the intersection of the tangents, no? PI. Let's call it PI, all right? And then this is known to have an elevation of 152 meters. So we will connect it with a single parabolic curve. So that's what we call symmetrical. So this is one parabola, not a compound parabola. A compound parabola will be used if, for example, if you know the elevation of this point, and this elevation and grade is known, elevation and grade is known. So you don't have control above of the curve. So you, in that case, you can use, or there might be a need to use a compound parabolic curve. We call it asymmetrical. Okay, so here we'll use a symmetrical, a single parabolic curve. Okay, so that's a parabolic curve. Now, what are the important properties of parabola? All right, this is the important geometric properties of parabola. A parabola changes in slope at a uniform rate. Well, to show that, all right, so we know that the equation of the parabola opening up or down is in the form y equals kx squared. If it opens down, it will be negative kx squared. So anyway, that's just similar. It can be covered by the value of k. So if you take the slope of this parabola, the slope of the parabola y prime is 2kx. So what does this tells us? So meaning the slope of the parabola is directly proportional to the horizontal distance, directly. So meaning the slope of the parabola changes at a uniform rate, uniformly, varies uniformly with the distance, So meaning from 3% moving 1 meter, it will change. So every 1 meter, there is a constant change in slope. So that is very important. That's the parabola. Another property of parabola. If two tangents of a parabola are drawn, these tangents, two tangents at any point, these tangents will always meet halfway between the points of tangency. So the tangent through PC and the tangent through PT, they will always meet halfway between the two. So meaning if this is 320, this distances here IL over 2. The same. That's the property of parabola. You cannot take it out from parabola. It's always like that. That is if that is a single parabola, except if this is a compound parabola. So for the same parabola, it can always, that's always the principle. All right, the behavior of a parabola. Okay, so let's call this point A, and that is point B. This is our summit. All right, so let's call it point D. Okay, so what's the formula for the elevation and the stationing? Now, there is a formula for this, but, well, if you have discussed or if you have studied the shear and moment diagram already, there is no need to memorize the formula. You can use here the grade diagram, very similar to a shear diagram. So, look at this. All right, so we will locate that. Let's do the grade diagram. Our premise is this one. The grade slope is directly proportional to the distance, okay? The grade at A, at PC, is 3%. 3%. The grade at PT is 2%. Okay, so 2%. The grade at the summit, of course, being the highest point, the peak, is 0. Okay, so if you plot it here, it will be somewhere here. And according to this, the grade varies directly with the distance. So meaning straight line, linearly. So this is your grade diagram. Yeah, grade diagram. It's very obvious. Okay, so as what I mentioned before, if you have studied shear and moment diagram already, you can be reminded of that. This represents the shear diagram of a uniformly loaded beam, and the parabolic curve is the moment diagram. Moment diagram. So that's it. Very the same, because this is we're talking here of geometry, and this is the behavior of parabola. It changes in grade at uniform rate. So with that known, we can easily locate the summit, the location of the summit. Let's call this S1, and we can solve that using ratio and proportion, the similar triangles. This big triangle can be similar to this small, or we can do it like this. Okay, S1 is to 0.03 as 320 is to 0.05. Did you get this? S1, this is the S1, is to 0.03 as the whole triangle, we will draw it from here. The whole width here is 320 is to 0.05. Okay? That's much easier than using this small triangle. Okay, so you can solve S1 as 192 meters. All right, so 192 meters. There's a formula for that. L, G1L divided by G1 plus G2. But that formula can easily be forgotten. But if you know this principle, it's very easy to recall. Okay, so we know na S1, we can now have S2, that is 320 minus 192, that's 120. And we can now compute the stationing of the summit. All right, so the stationing of the summit is station 10 plus 100 plus 192. So that will give you 10,000 or 10 plus 292 meter. Okay, so we now have the summit of the curve. Next, the elevation of the summit. Okay, to get the elevation of the summit, we need to know this height, because it will be the elevation of PC plus this distance, vertical distance. That's how we will do it. But we don't have the elevation of the PC yet. But what is known here, although this is a very unusual, what we know is the elevation of the PI. Normally, we have the elevation of the PC, but this is just an illustration. So suppose PI is the one known. So PI is 152. So we need to get the elevation of the PC. So how do you get the elevation of the PC? Right? So we need to know this distance, this height here, vertical height. Let's call it H1. To get H1, take note, we already know this one. Okay, 160. And we know the slope of this curve. The slope is 3%. So what is the slope? The slope is rise, H1, over 160. Okay, slope is rise over run. So knowing that, then H1 is equal to run multiplied by the slope. So your H1 is equal to 160 times 0.03. So that's 4.8 meters. This H1. Rise over run. Slope. All right. Then knowing H1 now, makukuha na natin yung, we can now solve the elevation of PC. So elevation of PC will be 152 meters minus H1. Okay, this is it. So that's elevation 147.2 meters. Okay, so our mission is to get the elevation of the summit. So we will be solving YD, the vertical distance from PC to the summit, which is, I called it point D. So how will you solve that distance? Okay, take note, we already know the elevation of the PC. Or we call this the beginning of the vertical curve, BVC. The beginning of the vertical curve. There are so many notations to that, but it means one thing. So beginning. Or VPC also, beginning of the parabolic curve. Ayan, beginning of the parabolic curve. Okay, so to solve for YD, okay, to solve for YD, so let's recall the property. If you have remembered the property of the shear and moment diagram, there is this property that the area of the shear diagram, because this is the shear diagram, if you relate it to load, shear, and moment diagrams, the area of the shear diagram between any two points represents the change in moment between those points. Okay? So in this case, the area of this gray diagram between any two points represents the change in elevation of the curve. So meaning the area, this area here, I changed the color so that you can notice. This area, let's call it area 1. Okay, that will be equal to your YD because this is the change in elevation from A to D. So area 1 equals YD. And area 1 can be solved easily. It's a triangle. So area 1 is 1/2, 192 times 0.03, and that's 2.88 meters. 2.88 meters. Okay. So knowing YD, then we can now solve the elevation of the summit. So that's 147.2 plus 2.88. So that is 150.08 meters elevation of the summit. All right, next. This one, I put it here. Next, let's determine the elevation and grade of the curve at station 10 plus 200. So that will be 100 meters away from PC. So that's right here. Let's call it point E. 10 plus 200. So how do we solve the elevation? The stationing, no problem. You just add. Anyway, the stationing is already given. To get the elevation, normally students would use here square property of parabola. But no need to do that. So just project it to the grade diagram. Okay, this is it. This one. Okay, by principle again, the height of this line, that red line there that I highlighted, I colored red, that's already the grade of the curve at A. Because this is the grade of the parabolic curve at any point of that curve. So the grade of the parabola at A is simply that is G1, GE. So this is 100 meters and this should be 92 meters. You can solve GE by proportion. By the way, required. It is also required here to solve the grade of the curve. Okay, so the grade of the curve. So GE is to 92 meters. So we can use ratio proportion. This is to this as 0.03 is to 192. All right. So we can solve our GE. So that's in decimal, 0.0144 or that's 1.44%. So we have already answered the grade of the curve, 1.44%. Okay. And finally, the elevation of that, okay, all we need is the difference in elevation. We already have the elevation of the summit. If we can solve this vertical height, this distance, then we can solve now the elevation of it. So how will you solve that? Okay, you get this area here. Let's call it area 2. Okay, and that area, as what I have mentioned before, that represents the change in elevation between these points, D and E. This is it. This is your area 2. Okay, and that area 2 can be solved easily. That's a triangle. 1/2 92 times GE. That's your area 2. 1/2 GE 0.014. Okay, this is rounded up, by the way. So the value with 4 significant figures is 0.01438 times 92. That's 0.661. That area, that's shaded area there. All right, so knowing that, then we can get now the elevation of the point E. So that's elevation 150.08 minus 0.661. This is it. So that gives us 149.419 meters. Okay? Did you get it? Anyway, you can rewind the video. You can play it again. Okay, so that's it. And the third question. The elevation of end of vertical curve, PT or EVC. The elevation of the PT. Okay, this is easier. This is similar to how did we get the PC. So all you have to do is to get the vertical distance from the PI to PT. And that is, okay, we know the slope of this grade, 2%, and the horizontal distance is known. Then we can solve the vertical distance. The vertical distance is 160 times 0.02. So I will not know lang the figure here or the height, but it can be like this. That's 152 minus the vertical distance. That's 160 meters times the slope. This is it. And that is 148.8 meters elevation of the PT. Okay? Or another way, just to present to you the principle, okay. For example, if what you have is the elevation of A, how will you get that PT without getting the elevation of PI? So you can do that. Once you have the grade diagram, the difference of elevation from PC to PT is, of course, the area, the total area of the grade diagram. Your area 1 is already known. Your area 1 is 2.88. This is it. Area 2 can be solved here. What is this area? I will call it area 3. That will be 1/2 128 times 0.02. That gives you 1.28 meter. So that's negative because that is below. That should be negative. All right. So the elevation of PT using this elevation here will be 147.2. Okay. Sorry. 147.2. This is 147.2. I forgot to write. Okay, so 147.2 plus 147.2 plus 2.88 minus, the drop here is area 3, minus 1.28. Okay, that gives you 148.8, which is the same answer with the previous. Well, I'm not making the solution long. I'm just explaining to you how to use the grade diagram. This is very useful and much easier because you don't have to recall, to memorize the formulas, which sometimes we don't understand. That's the worst thing. Okay. So now, well, if you want a more flexible solution, but this needs a formula, but we will discuss the formula. You can use analytic geometry combined with a little calculus. Maybe when you hear calculus, no, you may have bad experience of it, but it's very easy. Okay, consider this one. By the way, before I go to that, if in case you want the elevation of the center of the curve, this one here, let's call it point C. Okay, to get that, you can solve this one. There's a formula for this. This is normally denoted with capital H. The offset between the PI and the curve, the vertical offset. Okay, that is given by the formula L/8 times the absolute value of G1 and G2, or we call this the change in grade, G1 minus G2. So substituting the values, you will get exactly 2 meters. Yeah. Or if you want, you can solve, if you forget this formula, you can solve that H using the grade diagram. So if you put that value, so by the way, this is now elevation 150. Okay, that will be right here. This one, a very small portion here. So in that portion, this will be 160, so 192, so this should be 32 meters. 32 meters. So if that's 32, we can solve this height here by proportion. 0.03 is to 192 as this grade is to 32. That will give you 0.005 or 0.5%. So the grade of the curve at the center of the curve is 0.5%. Yes, 0.5%, 0.005. So we can now, you can now solve the area of this small triangle, this very small triangle here, 1/2 32 is 0.005. That will give you 0.08. So therefore, the difference in elevation from here, D to C, is 0.08. So correct, 0.08 or 150.08 minus 0.08, that gives you 150 meters as what we have in using this formula. Okay, so that's an additional information. Okay, now let's try using geometry. Now, this is the parabola, single parabola. If we get the equation of the parabola and if we have our center, our origin at the PC for convenience, so at any point of the parabola xy, any point, this is any point, this is x, this is y, the parabola can be written, or the equation can be written as y equals ax squared plus bx. There is plus c, but since this is already your origin, the constant there will be 0 already. Because obviously when x is 0, y is 0. That's why the constant here is 0. So we have two unknowns, A and B. But normally what we know are the slopes. So if what you know are the slope or the slope at TC and at PT, then you can express this in terms of the slope by getting the first derivative. The slope of the parabola at any point, we know it's y prime, the slope of the curve. The first derivative of that is 2ax plus b. So meaning this is the slope of the parabola at any point. All right. And we know that at A, meaning when x is 0, the slope is g1. That's the beginning of the curve. When x is 0, y prime is g1. Therefore, your b is equal to g1. Okay? And we also know that when x is L, at the end of the curve, when x is L, the slope is g2. So when x is L, that will be at point B. When x is L, the slope is g2. Substitute that here with b already known, then you can get your g2. It will look like this, 2al plus g1. Okay, g2. So with that known, we can now solve the value of a. That is the value of a in this formula. Okay, so I wrote it here. This is the equation of the parabola with grades g1 and g2 known. The equation is y equals g2 minus g1 over 2l x squared plus g2x. And the slope is equal to this. Again, I have to stress this out that your PC is your origin. 0, the elevation of the PC is 0. So do not misuse that one. Okay, knowing the general, then we can have the B value and the A value. So this is now the equation of the parabola. Okay, well, the advantage of this is at any distance x, you can get the elevation without drawing anything. That is the good thing about this. In actual practice, if you want to lay out the curve, you use that one, then you don't have a problem anymore. Okay, the slope, no problem, y prime, yeah, ito yung equation, the equation of the slope. Okay, let's try using it. If you want to locate the summit, we know at the summit, the slope is 0. At the summit, y prime is 0. So with y prime 0 here, you can solve the value of x. And the value should be 192 meters. That's the same value we have before. And how about the elevation? So we will solve the value of y. So when x is 192, substitute it in this equation, x 192, you can solve the value of y. That's 2.88, the same value before, 2.88. And at station 100, so when x is 100 meters, that is a station here, 10 plus 200, 100 meters from A. So when x is 100, you can solve the value of y, 2.219. Right? So therefore, the elevation of that point is 147.2 plus 2.219. That will give you 149.419, the same value as what you have before. Okay? So thank you so much for spending time watching this video. I hope you learned. You learned something. Again, don't forget, if you want to get updates of our video, please click subscribe and please click the bell to have regular updates. Don't forget to leave a comment on this video. Thank you so much.